Since the dawn of time, mankind has observed the intricate rhythm of earth and sky, and utilized the behavior of the heavens to form our notions of time and space. The most important celestial body to primitive man and navigator was the sun. Today, we discuss how two simple, educated observations of the sun are enough to place ourselves on the globe with extraordinary accuracy. These calculations are possible due to the formulaic motion of the Earth in relation to the stars, the moon, and the sun. Even the earliest of civilizations made note of these observable patterns and put this knowledge to a number of uses.
The Sumerians, dating back to 2000 BC, are one of the first cultures recognized for their use of the sun, the stars, the earth, and the moon to determine location. They identified constellations in the sky and used those to determine specific times of the year. Shortly after the Sumerians, the Babylonians, dating back to 1100 BC, observed the sunrise and sunset to document variation in daylight. The Babylonians also invented the degree system to determine positions in the sky. According to the Babylonian calendar, night and day started with sunset. The night was first and then the day. The Greek culture from 2000 BC through the 2nd century brought many advancements in the field of astronomy, specifically through their study of the sun's movement across the sky. They were recognized with discovering that the world was actually round. This was discovered by Eratosthenes when he measured the angle of a shadow cast in Alexandria, Egypt, at the meridian passage of the sun. Other Greek scholars include Aristotle, Hipparchus, and Ptolemy, who developed the latitude and longitude system that we use today.
Jacob ben Macher, a Jewish astronomer of 14th century Provence, invented the cross staff, a tool used to obtain the altitude of the sun. The transversal would slide up and down on the main staff in order to measure length. John Davis, a 16th century navigator, invented the backstaff. Wooden, it was made up of two arcs. One vane allowed accurate sighting of the horizon, while the sun showed a shadow on the other vane. It was used to find longitude and latitude from the sun. John Hadley and Thomas Godfrey invented the octant in 1730, which later became the sextant. This tool measures the distance between two objects. For navigators, it was used to measure the sun's altitude by measuring the distance between the sun at meridian passage and the horizon. This tool is still in use today. John Harrison, a British clockmaker, invented the seagoing chronometer in 1764, which used Greenwich Mean Time, the local noon, and spherical trigonometry to determine longitude at sea. By international agreement, the prime meridian was established as the meridian passage of the sun through Greenwich, England, in 1884.
Our hypothesis is that you can find your latitude and longitude using measurements made from the sun. So let's put that to the test. Here we have an equation relating latitude to the arctangent of negative cosine of d over 2, we'll talk about what d is, divided by the tangent of the solar declination. So let's talk about what d is. First of all, we made measurements here in Cambridge, Massachusetts of the sunrise, where we found that this rising solar azimuth is about 112, and the setting solar azimuth to be about 252. So d in this case is actually this space here, which is found finding the degree separation between the rising and setting solar azimuths, and then subtracting that from 360. So in this case, it's 225. So plug d into this equation here, same equation as up above. So we have cosine of 225 divided by 2, divided by the tangent of the solar declination, which remember is found using this chart. So let's look at our day of the year. We're about here, trace it down to the line, and trace it over. And actually, the number lies somewhere between negative 20 and 25. Today, it's negative 22. So we put that in the equation and solve, and in fact, it gives us 43.45 as our predicted latitude, which is pretty close to 41.78, which is where we are here in Boston. So we're only off by 1.665 degrees. Not bad.
Once we have made these measurements and have accounted for corrections, we can take the time directly between sunrise and sunset in our local time zone. This is the time of meridian passage. We then must express this time in UTC, which is a simple time zone conversion. We must also make a correction for the equation of time, which is unique to the day observations are made. We now must compare this value with 12 o'clock noon in Greenwich, England. This difference, expressed in degrees, where 1 hour equals 15 degrees, gives us our calculated longitude. As can be seen in our data, we managed to be fairly accurate in our calculation of latitude and longitude considering our primitive approach. That being said, a number of difficulties caused our estimated positions to deviate from our actual positions by, in some cases, a couple of degrees. Finding our longitude was somewhat complicated by inclement weather, which often blocked out the sun, and obscured horizons, which we tried to account for with degree approximations. Latitude, on the other hand, was a challenge due to inaccurate compasses and unideal places in which to take compass readings. Furthermore, out of practicality, we found the solar declination through an approximation. Thus, our measures of sunrise, sunset, and azimuth, as well as our subsequent calculations, were not perfect. However, the fact that we were able to roughly plot our locations with merely a watch and compass is undoubtedly an impressive feat.
In conclusion, we found that our hypothesis that location can be found using sunrise and sunset was largely accurate. Indeed, although modern technology has afforded us with more precise methods of finding location, this tried and true technique of the primitive navigator still proves to be sufficiently effective with a little effort, intelligence, and attention to detail. Thanks for joining us, and we hope you found the presentation enlightening.
Well, I had a dream, I stood beneath an orange sky.